Good evening, sir.
Good evening.
Today's session, good evening, everyone. So today's second session is by Dr. Sudhan Majhi. He received his MTech degree in Computer Science and Data Processing from IIT Kharagpur in 2004 and PhD degree from Nanyang Technological University, Singapore in 2008. He was an assistant professor jointly with the Mathematics and Electrical Engineering Department, IIT Patna. He also was an associate professor with the Department of Electrical Engineering, IIT Patna. Currently, he is an associate professor of Electrical Communication Engineering with IISc Bangalore. His research focuses on estimation and detection. He is a fellow of Sir Vishwavaraya Young Faculty Research. He has a postdoctoral experience with the University of Michigan, Devon, MI, Institute of Electronic and Telecommunication, Rennes, France, Nanyang Technological Institute, Singapore. He is currently a senior editor of IEEE Transaction of Vehicular Technology and IEEE Communication Letters. So over to you, sir. You can start with the session, sir.
Good evening, everyone. Thank you very much for the introduction, and thank you very much for giving the invitation for delivering this lecture on intelligent reflecting surface. And let me come to the introduction for the intelligent reflecting surface. So as we see, am I audible properly?
Sir, you are audible, sir. Yes, sir, you are audible. Good to
go. So you can see that in the era of 5G, beyond 5G and 6G, there are tremendous increase in data traffic. So the enhanced data rate, data security, spectrum efficiency, power efficiency, computational complexity efficiency. So those are very, very important parameters, and based on those, that 4G, 5G, 6G all are defined. For example, for 5G, so we need a higher data rate. We need a enhanced data rate. We need that massive type of industrial communication, and also we need the low latency. So this is one way we define 5G. Similarly, if we talk about 6G, so 6G means we are integrating some more parameters, like we are trying to bring the intelligence into the picture, and ubiquitous communication, IoT, all these things are coming to the pictures. So you can see that, and most of the time, if we need to increase the data rate, then we need a very power hungry system like MIMO. We need more number of antennas. Then more number of antennas means that RF, and more number of RF chain. And it is well known that RF chain are more power hungry. And not only that, if we want to increase number of antennas at the base station or at the transmitter, we need to have also the CSI overhead, the channel state information we call CSI. So this has to be feedback to the receiver, and that another bottleneck means how that huge number of CSI has to be estimated at the receiver, and those again need to be feedback to the base station. So this is not very easy job. So if we look only in terms of data rate, then we need that very more number of active RF chain. Now the question is that, can we reduce that? The number of RF chain will be less, but still we can achieve that data rate. So that is the one main agenda that we are coming to this intelligent reflecting surface. So the other way, you see that why we use MIMO. We use MIMO to achieve the diversity. Diversity gain means if there is an obstacle at receiver, there are multiple paths and most of the paths are up, there are some kind of obstacle. Then to remove this obstacle or remove this shadowing, what we can do? We can pump more power to by the multiple antennas. So this way, that whatever shadowing area are present or obstacle areas are present, those can be nullified, or those can be those position can be served by more power MIMO system, but those are not power efficient. You see my second bullet, we also mentioning that we need a more power efficient. So this, then more power efficient means we cannot transmit more MIMO. Okay. So then now we are finalizing two agenda. One is that we will not transmit more power, means we will not have more MIMO RF chain, and still we can able to transmit high data rate. So if you see that intelligent reflecting surface, there is two objectives at this moment. Later we will explore little bit further. One is data rate, one is power efficient. Is it clear? If this so, now this is a intelligent reflecting surface. So let us spend some time on this. What is intelligent reflecting surface? All these things. So let me. Now it is visible now?
Yes, sir. It's visible, sir.
Yeah. So you can see that this is a intelligent reflecting surface, and these are entire things are intelligent reflecting surface. Now these are the elements. Okay, and this is a controller. That the controller get the signal from somewhere else. We'll discuss it later. And then what it does, if any signal come to this surface, then it gets another phase and reflect to particular direction, and this direction is defined by this controller. This controller decide that what will be the phase of this element and what will be the phase of this element, and along with this also decide amplitude. Let's say this transmitted power P, and here the reflection also will be having phase and amplitude. This amplitude can be also decide. So but these elements, they are passive element, and it has some kind of metallic and dielectric particles, so it has some property, and this is the main things that if signal is impinging to any element, it will get phase and it will get another amplitude and reflect the signal to particular direction. Now so you can see that it has a large number of scattering element. So in this case 1 2 3 4 5 6 7 8, and 1, 2, 3, 4, 5, 6. So it is a 8 cross or 6 cross 8 elements. And the response of coming incident waves, that is either it will be reflected. So in this case, reflected, and some case it may not. So it's come and then it does not reflect anything. So it is called a, this one is reflected, and this one we are not getting any signals. So we call it absorbed. Okay. And this reflection, absorption, all depends on the type of material, the size of material. Size means what is the width and what is the height. Based on that, we can also design the loss and many things. And now if we look, it has many properties. One is called the reflection. So signal receive and reflect. Another is called the refraction. So when signal is coming and then it reflect to the other direction. Then absorption. If the signal come, signal will be absorbed fully or partially. Focusing, you see the parallel signal will be coming and then it will focus to a particular direction. It has also polarization property. So it has one polarization. After reflection, the polarization will be changed. You can see that polarization has been changed. And after the incident, the signal will be splitting. In this case, this is a splitting to one direction. This is splitting to another direction. Then also they do the analog processing, then collimation. So many properties it has. So we'll discuss also some property later. But before, let us see that what is this element, how it is made, and how we change the coefficient of the signal. So you can see that it is a 3 layer, layer 1, layer 2, and layer 3. And this is called a outer surface. It is actually consists of meta materials, and which actually interact the signal, the impinging signal reflect by this layer 1. And layer 2 is called a is a protected layer, which avoids signal energy to be leakaged. So this is a second layer, and it is mainly made by the copper plane. And then most that inner is called a control circuitry, and which is mainly control the signal, that whether it will be off or on, and based on that the signal will be reflected with particular phase and amplitude. So you can see that this is the whole IRS, and it has also different name. IRS we called RIS, reconfigurable intelligent surface. We call LIS, large intelligent surface, and many more name is there. But we prefer mainly IRS and RIS. And it has a 16 cross 8 elements. Now one element, this is a one element. You can see that broad, and it has a varactor diode. And how this diode we made, if you can see that this is nothing but it has a 2 diode. So one is and this one, once you signal incident the signals and signal, there is a outgoing signal. And how does it work? The reflection coefficient is equal to this equation. So this is called a intrinsic impedance of mth element for when bias voltage is V. This is a bias voltage V, and this is a characteristic impedance. So intrinsic impedance minus characteristic impedance, and then intrinsic impedance plus characteristic impedance. So that is create a reflecting coefficient. So if we have a voltage V, and then there is a circuit, you can see that that this is a total circuit, how we generate a incident signal and impedance signal. And this is generated by equivalent circuit of on and off, and this on and off varactor diode take very minimal power. That's why we call it passive. This is not at all RF, but in the case of relay, cooperative communication or relay or even MIMO antennas, we use RF chain. But in this case, we use very simple varactor diode, which need very minimal power. And this can, the capability of changing this phase can vary from 0 to 2 pi, and amplitude variance is from 0 to 1, but usually we use constant 1. But this is for the passive IRS. For active, there is another case we will not discuss here, is called active IRS. So even they use amplitude greater than equal to 1. So this is called the active. But for the case of passive, it varies from 0 to 1. So this is the main property of IRS. And the people who are wireless, that antenna design guy, they or antenna research community, they design such kind of internal structure of IRS. But as a physical layer or communication guys, they use this structure, and then they utilize this structure and design the transmission protocol, how to increase the data rate, how to increase the diversity gain, and how to provide the better assist bit error rate performance. So as I said that among total M elements, each will have different reflecting coefficients. So it is not that all elements means I'm talking about this is elements. This is a elements, and it's not that all elements will be having the same phase and same amplitude. So they may have different amplitude and the different phase, and that way they can direct the overall signal to particular direction or can focus to particular point. Now these reflecting signals of the different phase may perform constructive and destructive. For example, let's say there are some elements, and now we'll be having some phase of this one, and this one will be having another phase. So, and this is, you can see that this is phase of this one is different, amplitude is different, phase and amplitude of this is also different. Now they are impinging here. Now, and this is a user equipment. Now, if the user equipment is here, then the phase of this will be different and amplitude also will be different. So this way, if you change the phase and then amplitude, then you can focus the directed signal to the different point. So this is called the by phase shifter and impedance different elements. So that change the amplitude, and also changing the delay also we can change the direction of the transmitted reflected signal. And then one thing, that whatever the phase we are introducing at the elements, so those phase need to be compensated at the receiver. So this is a user 1, UAE 2. So whatever the phase we are provided here, those has to be compensated. And what phase will be given this one? So there is a controller. Usually it's connected to the and also connected to the base station. So base station get all the information. Base station have all the information about the user location, the distance of user from the IRS, and based on that, the base station decide what will be the phase and what will be the amplitude, and this information passes to the controller. Then based on this data from the base station, controller change the phase and amplitude and serve the users. And this mechanism is called a beamforming. Now, how is the model? The phase shift introduced in the IRS is generated by theta, and this IRS incorporated with the varactor diodes, and this theta can be continuous and also it can be finite value. So in the case of finite value, it should have PIN diodes for finite values. So finite value means, let's say 0 to 2 pi, right? I can give 10 phases. Okay, then I need a pin diodes, 10 pin diodes. So 10 pin diodes means, that 10 value will get, right? 10 value will get, and based on that we need a pin diodes, and they will be changing, and based on 10 pin diodes means how many diodes we need. If I off and on, we need 2 to the power 3, 2 to the power 4, 16, right? 16 pin diodes, then we can get 10 different phases. If we 8 phases, then we need only 2 to the power 3. So we need only 8 pin diodes. So this way we can get distinct discretized phase. So mathematically, if there k pin diodes are implemented, then this n possible shift phase, this is this one, n should be less than equal to the power k. So that's why in this case n equal to 10, and it should be less than 2 to the power 4. Okay, and since IRS can divide it into 3 types, we'll show how these 3 types of IRS responds to the incident signal. So 3 types, I means, there is a 3 way we can divert the signal. One is called the reflecting type, one is called the transmissive type, and other is called the hybrid type. So what is the reflective type? So whatever the signals incident, so in this case X be incident signals and Y is our reflective signals, and then the reflection coefficient is this one. This is a response of the IRS element. So what is there? So you can see this gamma actually nothing but it belongs to 0 and 1. So this is contribute in terms of amplitude or energy, whatever you can say, and theta is the phase and x is original signal. So that output will be y equal to reflection coefficients plus reflected signal x. Okay, and this, if the gamma is 0, this means that signal is absorbed fully. Okay, if gamma equal to 1, then signal is fully reflected without any loss. So that is the significance of gamma. But in terms of the reflection response, we denote this one. So one is contributed by amplitude, the other is contributed to the phase. So this is called the reflective type, and reflection coefficient could be maximum 1, can be 0. That is for the passive IRS. But as I said, for the case of active IRS, this gamma could be, gamma belongs to 0 infinity. Infinity means that large number of reflection coefficient can be generated, and there are many what is going on in this active IRS. The other is called transmissive type. So what is called? Now, whenever signals impinging to the element, so instead of reflection, so it's transmitted through the IRS element. So you can see that it is the other side of this. This is a other side of the IRS element. So it is a transmissive to the element, and in this case also gamma, the response will be the same as the previous case. You can see that this is a response factor, and this gamma again could be 1, could be 0, and theta could be continuous and could be discrete. If continuous, then can be implemented by the Varadachter diode. If it is a discrete, then can be implemented by PIN diode, and PIN value we know. The other is called hybrid type. So what is this hybrid? You can see that one part will be reflective and other part will be the transmitted. So the entire signal energy, they divided to two parts. So one is called the transmitted signal, other is called the reflected, and then coefficient is depends on that. So you can see this is a reflective coefficient, and this is a transmitted coefficient. And now from here, if you want to make only to reflective, then make beta tends to infinity, and if you want to make it is fully transmittive, then put beta is tends to 0. So by changing the value of beta from this equation, one can provide transmitted signal and reflective signal, which is nothing but a hybrid, or one can just simply convert it to transmitted signal and then or reflective signals. Okay, and this property, hybrid property, help to put this IRS on the rooftop of the house or rooftop of the big complex. So here that signal could be transmittive or transmissive types of nature, and signal will be receiving from the outside and reflect or penetrate to the house or to the auditorium or many big complex. Okay, and this property we use for the also for the satellite communication. Okay, so that is a different things, one type of application. So now this is a very good characteristic, as I mentioned that IRS has so many elements, and now that what could be the size of the elements. So now let us, 3 studies we have taken here. So size is this one. So in this case, this is a lambda and this is a lambda, and this one is denoted by this one. Okay, what study? So this is size of the element. This is the size of the element, and now we want to see that path loss. What will be the path loss if the element size is lambda cross lambda, and what could be the path loss if the element size is 2 lambda, 2 lambda and 2 lambda, and this is denoted to 2 lambda is this one. Okay, and other thing is that size will be the lambda by 5 cross lambda by 5, and this is related to this one. Now let us talk about the first one. This is the first one. You can see that and because the signal will be reflected and then reflected to the element, and from there it can travel to 0 degree, 10 degree, 20 degree, 80 degree. So that user's location could be ranged from 0 to 80 degree. Now you can see that this is a loss. So you can see that it is around minus 12 loss across the every degree. Means that if you divert your signal to 0 degree or 20 degree or 40 degree or 80 degree, almost the loss is same, and this is a minus 12 dB loss. Now let us talk about this second one. The second one, the size of element is 2 lambda cross 2 lambda. Now we can see that when 0 degree incident, that incident angle difference between the reflection, impinging and reflection. So that time loss is very good, means 60, very minimal loss, 60, it's a good. And when above the 90 degree or 100 degree, 90 degree or 100 degree, that time also loss is very minimal. But when the loss is around 40 degree or 20 degree or 60 degree within this region, the loss is very significant. You can see that this is the loss region. So it is around almost minus 1 to minus 5 dB loss. So which is very significant loss. But if we talk about this third one, is very small, lambda by 5. What is the lambda? Lambda is a wavelength of the frequency, and in this case loss is constant, fine, and also it is a minus 40. So you can see that if you compare these 3, then we'll find that minus 38 loss is a good one, because it is a constant and irrespective of the phase difference, it's giving the constant loss. So it will be very easy to design your receiver. It's very easy to design your automatic gain controller. But if we use this 2 lambda by 2 lambda, you can see that it's loss when 20 to 60 degree phase difference. At that time, there is a loss is huge. Okay, so this kind of and this intelligent reflecting surface, it's very important when people design the this IRS elements. it's a very specific. You cannot design IRS for wide range of frequency. So some IRS is designed for a specific bandwidth. For example, for 2 to 4 gigahertz, what type of IRS is needed. If you change the frequency, then that there will be different type of IRS is needed. Otherwise, you cannot generalizes the loss of the signal. Okay, and there is another important topic for the, so most of the whatever we discussed, they are the positive side, except this one. This is we need to design IRS very cleverly so that it will not have varieties of loss, or the loss would not be very high. But other problem, this is a main problem, this when we put some IRS element here, and there is a base station and there is a user equipment. So during this path, you can see this is a path and this is a path. So there is a two path. When we receive a signal at the UAE, so there is a two wireless medium, this one and this one, and we get some kind of fading effect from this path. We get also some fading effect from this path, and that's why it's called a double fading effect. And there is a two channel, it's called a cascaded channel. So this is another problem, that estimating this two cascaded channel and this two double fading effect. For example, let's say we are having a Rayleigh fading channel. Now if we get a fading effect from 0.2 and we get 0.1 from here, in the rare cases, not all the time, then overall fading effect will be 0.2 into 0.1, nothing but a 0.002. So no, okay, 0.02. You can see that this fading is very, very minimal. So, and this not always occur if we place the IRS element at particular location. So that is given here. You can see that we'll be getting the gain if we place, this is a source and this is a destination. Now we are varying the IRS element where we should put. If we put it 25, loss will be very, very high. If we put at 10, then loss will be this one. If we put at 5, then loss will be this one. And if we put at 55, loss will be this one. So there is some reason. I'm not going to very details direction. If you read, then only you can able to understand that placing this IRS element near to the source, this direction, or placing the IRS near to the destination, okay, always give a good channel gain. So this is a good for this one. This is a good. But if one can place in the middle of source and destination, then it will get a huge gain, that minimal gain from the channel, which will degrade the system performance. And why? I told that if we put in middle, this is a weaker path. This path is a weaker, and this is also weaker. So they may produce 0.2 or 0.3. This one also may 0.4 and 0.1. But if we place your IRS element near, this is no longer weaker. So it will be always will be around 0.8 value we'll get, and from here also we'll get 0. So 0.8, then next path means I'm talking about if it is put it here, then so near, right? So it will be 0.8, but this is a larger, fine, user equipment, but it may give 0. Let's say 1 or 2. So then you multiply, it will be still 0.16. Still it is greater than 0.02. So still it is a good compared to this one. Okay, so this is the main reason that but this is not a very good solution, because in this case it is bound to put your IRS either near to the source or either near to the destination. But we'll find any scenario that where we cannot put the IRS near to the source or near to the destination. Okay, so there are some other solution. So what are the key features of IRS? The key features of IRS are low cost. Why low cost? Because it's a passive most of the time. So does not require RF chain. If there is no RF chain, not power hungry. There is no need to have ATC and DAC. This is another power hungry, right? Analog to digital converter or digital to analog converter. If you use a decode and forwarding relay, it is a part of cooperative communication. So that time every DF need a ADC and DAC. So high spatial resolution. It's a large number of antenna elements, right? So they are in compact space. So it is a spatially continuous electromagnetic aperture. So it's a resolution. This is another one. This is another one. This is another one. This is another one, and they are highly regulated, because this one will give one direction, this one will give the another direction. So that create another advantage, and easy to implementation, because this designing this 3-layer IRS is very, very easy. Even you can have some kind of printing machine to create such kind of surface, and this surface you can put or place on a wall or on a signboard in a very thin layer, and you can paste wherever the obstacle is there, and you can put and create angle so that, and it can fixed, and you can just connect to the some like amplifier, so that repeater. You have heard about the repeater? So similar kind of, but it is a passive repeater, and also we can easily compare with the other kind of technology. So I'll provide this one later. So now you can see that another advantage of IRS. So here we have given one use cases. You can see this is a base station, and this is IRS element, and this is a user equipment, and there is a large building which is blocking the signal. So there is no direct path from base station to user equipment. You can see that there is no direct path. But if we place a IRS element and then incident the signal to this one and then provide the reflection, you can see that still we are getting a virtual path between the base station and user equipment. Okay, and also you can see that they are making a virtual communication, and this is called a shadowing region. As I at the introduction slide I mentioned, this area even can be filled by the power signal if we have very large antenna system, but that will be not power efficient. So that's why we are putting this IRS element. And this IRS element actually giving a line of sight communication, although non-line of sight place, but it is a providing virtual connection. You can see there is a connection, right? And it's a virtual connection, although we are taking by, so that's why we call it IRS provide a virtual, it is called a virtual line of sight. So you can see that it has some kind of applications as well. So in the case of physical layer security, so physical layer security means we try to provide security on the air. So when the signal is being transmitted on the air, that time we are providing some kind of security. So what does it mean? That this is a eavesdropper, and we are giving the phase and amplitude such a way that all the beamforming will be to these users. So these users will not get signal at all. If a eavesdropper do not get any signal in the air, then forget about that applying some kind of decryption and access the signal. So this is that we are creating a bottleneck in the air itself. Similarly, we can supply multiple users. So this is a users, this is a users, and we can use beamforming like massive MIMO we can create. We can have a lot of antennas and some off and change the direction so that we can supply multiple users. Okay, and it has a huge application in the cell edge communication. So what is cell edge communication? Let's say the users at cell edge suffers from high signal attenuation from serving base station, as well as severe co-channel interference from the neighboring base station. So in that region, we can install the IRS, and then the base station can transmit the signal to the IRS, and then IRS reflect the signal to the user equipment. And by this way, IRS also can increase the circle or service region of any base station. Okay, or cell edge can be increased further by placing more IRS, passive IRS. Okay, so instead of giving more base station, you can have one base station, and then cell edge region you can put many IRS, and then so that user equipment can get the signal properly without much power hungry devices. Okay, and here we have given some kind of example that there are many others technology which can be comparable with the IRS. For example, massive MIMO, as I told that massive MIMO also provide high data rate, but it is a power hungry, so very high energy consumption is very high. But IRS is very low because it is a almost passive. Relay, as I mentioned, relay is also used for cooperative communication. It has a active and passive, but still it need a high because it does not have multiple elements. It has only one antenna and one receiver, or 4-5 antenna, 4-5 receivers, multiple MIMO concept relay, but still it does not provide a much more power, need more power. And backscatter is very low, but it has a very specific use case, distance, but IRS can be considered as means very large distance communication device. Okay, and yeah, this is some application of IRS, and there is some counter competitor IRS, and you can see that IRS is a comparatively better power spectrum efficient technology compared to the massive MIMO relay and backscatter. Okay, and one more things. Okay. Okay, so what I wanted to mention here, that IRS is a one-way communication that which build up a channel. Build up a channel means modify the channel. So you can see that in this case, so there is a severity in the channel, right? When a building was there between two user and base station, we put IRS and give a virtual path. Means what? That there are some channel obstacle was there, and that obstacle we have removed. So it's nothing but we are harvesting a channel. We are providing a good channel, like good channel for communication channel. And this that how far it can because how many elements is optimum number of element and optimum power, all these come to the pictures, but I'm giving very rough things that that there is some kind of we need to derive that how many elements. Sometimes if you use more element, let's say 100 elements, it may not be required, because after certain number of elements you may not increase the power at the receiver. So finding optimum elements is also very, very important task. Okay, so we can give some kind of comparative analysis in terms of CISO, and you can see that this is a single input and single output receiver. Okay, so I have some time, right?
We have 30 minutes.
Okay, yeah. So you can see that system model of CISO, and this is a noise, this is a transmitted signal, this is a transmitted power, and this is a channel between source to destination. And once you know that, then we can easily calculate the capacity of CISO channel, which is this one, log 2 1 plus SNR. Okay, and now this is for the single carrier system. Now let us calculate the capacity for the CISO channel. Then we'll compare that which one is better, which one is providing a more capacity. So we talked that, okay, IRS is this, that, this has application, but theoretically also we'll see that how much capacity we are getting if we use IRS. Now you can see that there are n element, so every element will have a different phase. Now every phase will be multiplied some other signals. Let's say there are 4 signal, okay, x11, x12, x13, right? And then x11 will be multiplied 1 theta and this one. So then to do this one, what we do, we put if we want to multiply this one with the theta 1, theta 2 and theta 3, so what we can do, we can put theta 1 here, theta 2 here, theta 3 here, and then we can put x11, x12, x13, multiply, then we'll be getting all element wise multiplication, right? That the things we are doing here. So we put this theta and theta all diagonal elements, and this alpha is the amplitude, and then it's fixed, belongs to 0 to 1. And then you know that y will be, this is a direct link. We have assumed the direct link is there. If anyone think that there is no direct link, you can remove this SD. And this is a path, this path that as I said, there is a two path, cascaded path. This is a multi path, and this is another path. So that's why a matrix which has amplitude and phase, that those are multiplied with the SRT and RD. And this is a transmitted power constant for all, and this is a transmitted signal, and this is the noise. So now the rate maximization, what we'll do, because that whatever channel phase we are giving, and at the receiver, that has to be compensated, right? So whatever the phase we'll be introducing from here and here, that will be equivalent to that whatever signal, this is some phase, right? Phase will be here. So that has to be optimum. That's why theta n is a kind of rate maximization that we have to provide, because this one will be, we have to have a constructive things, right? So now if the receiver, if we provide this one theta n, then there will be constructive kind of communication. And then finally, I'm not deriving the holistic, all these things. You can get that rate will be this one. Now if we compare to this, that previous path, previous in this signal, there is a PHSD mod square, and if we compare, you can see that P is there. If I do the square, we'll be getting another term, P mod of HSD square, but after also we'll be getting some other extra term, and those are positive. This is positive, this is positive, and alpha is positive. So if you add something with some number, so still that SNR is larger than the previous. You can see this is only this term, but here we are getting some extra positive term, and these are the positive term. How we obtain? Just if we substitute those value here, then we will be getting this one, okay? And that indicate that IRS has a more channel capacity than the single carrier system. And even if we compare with also relay feeding, relay supporting transmission. So relay transmission is what? We transmit, again, this is a direct link, is this link, and this is this one is this link, this one, and this one is this link. So what we take? We take the minimum of bottleneck, right? If you know about the relay communication, so we take the minimum of these two. So this minimum of these two one. So minimum of whatever coming by SR. Okay, so okay, so minimum of this link, sorry, not minimum of this link, minimum of this one and minimum of this one. So minimum of this. So minimum of this we take, and then after simplification, I'm not going to the details of this derivation, but yeah. So this is the final things we are given here. So this is a CISO channel capacity, and this is a IRS channel capacity, and this is for the DF channel capacity. And some mathematical manipulation, we can prove that so this is the things we can get. So this prove that So I'm just skipping this. You can go through this. I've taken from journals, one journals, and then you can get it from here. Yeah. So this is the capacity. So CISO capacity, IRS capacity, and PDF capacity. So from here we can able to see that this IRS has the large maximum capacity compared to that other relay, and it has also some kind of simulation results. Let me have a look. And this one has taken some kind of so if one can plot this capacity, that's capacity with respective to the SNR, then only we could be able to this one. I have missed this one slide. Okay. So what is there that this one will be giving the better. So now this is some channel model that the 3GPP urban micro version. You know that every communication model there is some kind of channel model we provide. So this is a channel model that for based on this 3GPP urban micro version. So what is this? Now the total gain, that total gain will be in terms of distance. If you put the distance, then GT is a transmitter gain, and this is the receiver gain, and this is the distance, and this is a carrier frequency, and this is some kind of measurement we obtain from the measurement. As I said that every cellular system or every relay feeding, Rician feeding, or some kind of there are many type of path model. So in this case, this is a LOS path model, and this is a non-linear path model. So in this case, how to measure the channel gain? So this is the channel gain, and if we give the transmitter gain, receiver gain, and this then we can able to calculate. And if we provide the distance, let's say distance is some kind of 500 meters and FC equal to 2 gigahertz. If we put all this value, then we'll be getting some channel gain, and that channel gain we use as a reference level, and then we design the link budget or other things. And similarly for non-line of sight path, so this is a path model. So this model we have taken from here. Okay, this is and every communication, let's say Wi-Fi, Bluetooth, or cellular system. Okay, so there are some kind of specific model we use. Okay, and those model based on some kind of frequency, distance, and gain, all these things we measure. So if you go through Rappaport wireless communication, so there are many HATA model. So this is a specific type of model. In this case, this is a 3GPP urban micro version channel model. Yeah, in this case, we have provided the that transmit power, and then transmit power, and then that number of, if you change the source, and this is a destination, and IRS and relay. So if we come to this direction, this is a 10 meters D1, but relay is 80 meters, and this path is not given. So transmitted power needed to achieve rate equal to this is we need to achieve this 4 bits per second per hertz, and noise power we have considered this minus 94 dBm, and number of IRS element we are decreasing from 25 to 50. This is say in the decreasing order. So this is a 150, 100, 50, and 25. So now distance 40, 50, and 100, and you can see that transmit power needed for CISO increasing distance 100 meters to achieve 4 bits. You need to transmit this much of power. For DF relay, DF relay we need less power, but for the IRS, oh no, sorry, this is a reverse order. This is a 25. This is a 50. Sorry, 50. This is a 100, and this is a 250, 150. So if you increase the number of elements, then you need a less power. So in this case, you need almost 0 dB power for R equal to number of element is 150, but number of element is 25. Then still you need a almost 10 dBm. Okay, so this means that if we increase the number of elements, then we need to transmit less power to achieve some certain bit rate. Okay, and you can also see that that's all. And this is the another study for to achieve the 6 bits per hertz second per hertz. So to achieve this one, we need to transmit. Now relay, you see relay also need to increase the power. But as I said, no, that this is a kind of optimal. So for 80 meters case, this IRS work need a less power. So this is the optimum value for this IRS distance. So this is some kind of application, and then comparison with the CISO IRS DF. But there is some also practically or available in the market. IRS is not just theoretical studies. So in the practical status, NTT Docomos, so they have designed a prototype, and this prototype, if I'm not wrong, it is around 2019 or 2018 they have built it up. And MIT also has some kind of prototype, and they have some kind of studied, and they have some kind of white paper as well. And so this is a academic, and now Huawei also many others service provider, and they are having this kind of now almost initially it was mostly available academically to academic, but nowadays many industries also having the prototype, even they, and some already you can purchase this IRS element, and then you can do the test, and there are some easily available in the market also, this IRS test bed. And this is also greener wave. Okay, this is a greener wave, another Paris company. So you will find they are having that prototype. You can purchase there, but it is very costly. But even I think India also, some of the that institution, they are already built it up, mainly for the test bed purpose, not for the commercially deployable. So these are the status for this IRS. But apart from this one, if you want to look for so as I mentioned that that capacity, data rate, power, spectrum, and channel estimation is a very challenging task, because it has a not single channel, it has a cascaded channel, and estimating individual channel is very difficult. But sometimes there is a requirement of estimating individual channel. Individual channel means there is a 2 air link, right? One is base station to IRS, another is IRS to user equipment. I'm talking about this one, this channel. And so estimating overall channel is fine, but estimating individually is not easy. But sometimes there is a requirement for this one. Okay, and but apart from this, there are a lot of work also already started. This IRS assisted ISAC is another important task, important area of work. And then there is also RIM, SIM, many novel type of IRS. Means, here we are having only one IRS, but this stacked, that there are many IRS will be there. Is a kind of, this is a one IRS, this is a second IRS, third IRS. Now, if you combine all this IRS, then what kind of advantage or disadvantage you will get? So that those are these stacked intelligent meta surface. Then R full form is a RIM. You can see that one author is called Marco Di Renzo. So his group has so many new IRS. Yeah, I think that's all. But then I'll be happy to take some kind of question and answer.
Thank you, sir. Thank you so much. And I will repeat the questions for you. You can answer the questions, sir. First, I am just moving to the first question. How does the spacing between unit cell affect the phase shifting capabilities and the overall beamforming performance?
Repeat again.
How does the spacing between unit cell affect the phase shift? Spacing between the unit cell.
Can I see the question?
How does the spacing between unit cell affect the phase shifting capabilities and the overall beamforming performance? Means
Can I read the question?
In RIS, there are different types of unit cells. What is the space between the unit cells?
Oh, okay. Space between the unit element, right?
Yes, sir.
Yeah. So you see that usually it's supposed to be that that lambda by 2 some kind of things, no? that space difference. But initially, such kind of study was there that the difference between two elements should be lambda by 2. But nowadays nobody are looking this one, because they are increasing the number of elements, and among them some diversity or some independent row they are extracting, and those are enough to provide the better data rate or provide the better resolution. And also this mainly that space between two elements, all these things, it's come from the designing point of view. It will be not unique for if you're talking about that below sub 6 gigahertz or FR2. So those value will be changed. But usually it's lambda by 2, as per my knowledge. Yeah. Any other questions? Hello? Hello?
Sir, can you hear me?
Yeah.
Yeah. How can we mitigate mutual coupling between meta-atoms in RIS?
Mutual coupling?
Mutual coupling between meta-atoms in RIS.
Yeah, I'm not from this area. Maybe I'm from not designing antenna design guys.
Okay, sir.
I think this is a question related to the antenna design.
Yes, sir.
IRS, yeah.
Yes, sir. I'm just moving to the next question. What are the potential security concern with IRS?
So security concern, if we look at as a physical medium, I think it has a better security capability, because in the air it can stop the signal to the eavesdropper by changing the phase. So, and if you look at the upper layer security, I do not find any reference. But if you look at the physical layer security by IRS as a physical layer device, then it has a very good potential security compared to the existing physical layer security.
Okay, sir. I'm just moving to the next question. What are the requirements of an IRS unit cell for beam steering?
What are the
requirements of an IRS unit cell for beam steering?
So it need a location of user equipment, and also that speed. That mainly you need a location. If you have the location of user equipment and base station is fixed and IRS also fixed, so then you can easily calculate the difference, that impinging phase and outgoing phase or reflecting phase can be determined by the user location minus impinging signal.
Okay, sir. I'm just moving to the next question.
And also if it is active, if it is a passive, then reflection coefficient is fixed. But if it is active, then also we need to have knowledge of distance. Yes.
Okay, sir. I'm just moving to the next question. In transmission side base station implemented with massive MIMO, then between the base station and user IRS is placed. So how the energy consumption is overcome here?
Repeat again.
Transmission side base station implemented with massive MIMO, then between the base station and user, IRS is placed. So how the energy consumption is overcome here?
So it is not between, it is a, although between, but it is a like different angle. It is not placed on the line of sight location. It is placed such a way that it can create a line of sight between the base station and IRS, and line of sight between IRS and user equipment. So energy efficient means whatever massive MIMO we are putting at the base station, that is constant. So we are not playing, that power is fixed. But now placing the IRS, we can able to remove the obstacle. So we no need extra RF chain at the IRS. That is our main objective, that although you are having massive, that you are need to beamform to the IRS or somewhat. But still, if there is any obstacle, even after using the massive MIMO, that obstacle can be removed by placing the IRS.
Sir, I'm just moving to the next question. IRS is a periodic or non-periodic structure?
IRS is a periodic or non-periodic structure. Periodic, I do not get the what does it mean. Periodic, it is a kind of physically a device. So periodic, and the signal periodic come in the signal transmission. Okay, I do not get the question.
Okay, sir. We'll just move to the next question. What is the minimum number of unit cell required to achieve precise beam steering over a given angle?
This is already I have discussed. No, this is some calculation I have given, that if you know the power, that if you know the capacity, particular capacity, how much capacity you want to receive, then you can easily calculate this N. And that calculation already we have given in the slides.
Just going to the last question. How does the channels in IRS are characterized?
Just I mentioned no, that line of sight, there is a two type of channel gain: line of sight, non-line of sight. But apart from that, you can assume that from base station to IRS, usually we consider our line of sight, because we place the IRS at the such a place that it should have constant and constant distance and line of sight. So this is a rise and fading, or even sometime we can treat this as a deterministic signal, because RIS and base station, they are line of sight and beam focused is there, and more power we transmit particular direction. So you can treat also a deterministic signal. There are many assumptions, or you can directly, we can assume that rise and fading. But for IRS to user equipment, that could be like, could be rally, could be Raysian, yeah, anything could be happen. But if you want to talk the path loss, then based on line of sight, you have to adopt that channel model I describe, or non-line of sight channel model you have to describe.
Thank you, sir. That's it from the questions. Swarnima, you may hand over the
Writing session. It was a very knowledgeable and productive session, I feel, for everyone. We are like very thankful to Sudhan sir. Thank you, sir, for joining with us for the session. Thank you so much.